Okay, folks. Well, this lecture is going to be one of a series dealing with force, mass, gravity, acceleration, and motion. So we'll be looking at each of these areas up here. Now, one of the ones that are most prominent and probably least understood that relate to force, F equals mg, is mass. So we're going to start off really looking at mass, because I think it's really important that we understand what mass is in order for us to get an idea of what force is and what gravity is and what does gravity and mass do to create force. So let's have a look at what mass is. Okay, so now this is really a layperson's view of this. Okay, I could go into a lot of detail and then I would probably lose most of you. So I'm going to keep this at a lay level so that you can pin what I say to real life stuff. Okay, and I'll try to do that as much as possible. Okay, so let's start off. Mass. So this is it up here. And what do we mean by mass? I think probably the easiest way to describe what we mean by mass is to have a look at atoms. Okay, so over here I have a helium atom. So this is a depiction of it. So basically, if you look at the Bohr model of atoms, you'll have a central nucleus containing protons and neutrons, and that would be surrounded by a cloud of electrons at various energy levels. And in this case, helium having two electrons in that cloud, two protons in its nucleus and two neutrons in its nucleus. So basically, these two over here, two protons and two neutrons, create what's called an atomic mass, and this atomic mass is 4. So 4 grams per mole. Okay, I'll get to that, what that means later, into what mole it means later. The atomic number for this is 2, and the reason that the atomic number is 2 is because it has 2 protons. So an atom is an element is defined by the number of protons it has. So for instance, carbon has 6 protons, and that's what makes it carbon. Nitrogen has 7, and that's what makes it nitrogen. Okay, fluorine has 9, and that's what makes it fluorine. So if it had anything else, it would be something different. Okay. All right. So it's protons that defines what the element is. All right. The main thing is that we know how many protons there are, and we know how many neutrons there are in a particular atom, like for instance helium. So again, atomic number is 2, atomic mass is 4, because we have 2 electrons, 2 protons, and 2 neutrons. Okay. All right. So let's have a look at number 3. So I've sort of coded these so that I can chase them around the board. Okay. Alright, so we're going from here, over here, and we go over here. Okay, so let's have a look at this. Neutrons and protons have the same mass. Okay, so neutrons and protons both have the same mass. So therefore, it's easy for us to quantify. If you think about it, it's easy for us to quantify what is the mass of a proton. Okay, we can work that out because we know that they have the same mass, and we can work out how many atoms there are in a given amount of space. Because if we can work out how many atoms there are in a given amount of space, we can work out how many protons there are in that given amount of space, and therefore we can work out how many neutrons there are in that given amount of space, and because of that we can work out how much mass there is. Because electrons weigh so little, we don't actually need to count them, right? The mass of electron is so negligible that it's not worth us even worrying about it. So we'll just focus on neutrons and protons in order to describe mass. Okay, all right. So, and that is when we're working at this level. So once we start working at the quantum level, which will be another lecture after this, where I'll discuss these things in terms of quantum physics. Then when we're looking at that, then yes, the mass of an electron certainly is extremely important, and we'll have a look at that, because the mass of electron is important in terms of charge. So when we look at electric fields and how photons and that behave, then something as heavy as an electron would make quite a big difference. And when I say as heavy, I mean heavy compared to other quantum particles. Okay, all right, so let's have a look at this further down. So a mass of one proton, 1.67 by 10 to the minus 27 kilograms. So we already know what the mass of a proton is. 1.67 by 10 to the minus 27 kilogram. And we also know that a mass of an electron, as I said, 9.1 by 10 to the minus 31. So there's a vast difference between minus 27 and minus 31. You can see that this is that a proton, one proton, is incredibly heavy compared to an electron. So we're not really worried about the mass of the electron. So we're really just counting protons. So when we talk about mass, we're talking about the protons and the neutrons. Okay, so let's have a look at some other interesting things. So now, a mole of helium, so a mole is really a quantity, just like a dozen, a score is 20, a dozen is 12, while a mole is 6.02 by 10 to the 23. Okay, 6.02 by 10 to the 23. That's 6.02, 23, 6 and 0.02 and 22. 21 zeros after that. Okay, so this is a very, very, very big number. Okay, so what else do we know? We know that a mole of helium, which is this many atoms of helium, so we talk about them in terms of atoms because helium does not bond with other helium to create molecules like oxygen. So oxygen would come two at a time. And so would hydrogen. In fact, all the noble gas, all the reactive gases. There's 5 reactive gases: hydrogen, nitrogen, oxygen, chlorine, and fluorine are the main reactive gases that we use. And then, of course, anything in any halogen would also come in pairs. So it's these reactive gases that come in pairs. Well, helium's not one of them. Helium's a noble gas, and helium would come one atom at a time. So we wouldn't talk about a molecule of helium. We talk about an atom of helium. Okay, so we can work out that at 25 degrees C. So this matters. Temperature matters. Pressure matters. So at 25 degrees C, which is 298 Kelvin. We end up with, and at sea level, by the way, well, that's important, so have a look over here. So at sea level, 101.3 kilopascals or 14.7 psi. What do we get? We end up with 24.47 litres. So if you think about 24 or 25 litres, you know, that's quite a big balloon. That's sort of that size. 20 litres would make quite a decent sized balloon. That 24 litres balloon, if you just measured the helium inside it, it would weigh 4 grams, just 4 grams. Okay, so pretty much, in fact, 4.00. So very accurately, 4 grams would be 24.7 litres, provided that you measured this at sea level, so at 101.3 kilopascals. So and also it was at 25 degrees. That's how much helium you'd get, and it would weigh again 4 grams. Okay, if you brought the temperature down to 0 degrees C, so 273 degrees Kelvin, then you'd end up with only 22.7 litres. So you'd lose you're bringing it down that extra 5 degrees would lose about 1.6, 1.8 liters of gas. It would change. Okay, so you can see what's happening is the colder you make it, in other words, the less heat there is, maintaining the temperature, the less heat there is, then that is going to give you less and less volume. And of course, this is expressed really well by the combined gas equation. So this is not the ideal gas equation, which is PV equals nRT. The ideal gas equation, which is PV over T. Okay, that's the combined gas equation, PV over T. Combined gas equation because it combined the work that was done by Guy Charles and Robert Boyle. So the Frenchman Guy Charles and then the Englishman Robert Boyle. Both very, very famous people. Giants, if you like, whose shoulders we stand on, even today. So, now let's have a think about how big 6.02 by 10 to the 23 is. Well, I did a bit of work on that, and I thought, well, how can I explain to you how much that is? Because that is such a big number. Well, there's 1,300 million grains of ordinary beach sand in just 1 cubic meter. So think about 1 cubic meter. What's a cubic meter? What have I got here? There it is. That's a cubic ruler. It's even, I can't even get it across the screen. There it is. You can see most of it like this. Okay, this is a ruler. That's a meter. So it's a meter like this, a meter like that, and then a meter like that. So think about a block like this, a meter, and a meter down. That's a cubic meter. Well, if you counted all of the beach sand grain by grain in that cubic meter, you would end up with 1,300 million of those grains of sand. Okay, well, if you wanted to get this many grains of sand, 6.02 by 10 to the 23, if you needed to count 6.02 by 10 to the 23 grains of sand, you would need 500 trillion cubic meters. 500 trillion cubic meters you would need of those if you wanted to count this many 6.02 by 10 to the 23 grains of sand. So this is incredibly small. We're talking about something that's very, very small. Then it's this many, if you like, atoms that fits in this balloon, 24.7 liters. And remember, and these atoms are spaced far apart so that they are a gas. Okay, so this balloon is going to rise. It's less dense than air, so it's going to rise, and yet still it has this many atoms. Now, if you bring that back to, let's say, the size of a pencil. So you think about a pencil, a pencil like this, I don't know, about 7 or 8 inches, a 200 millimeter pencil, if you like, a brand new one, and made out of wood, so it's mostly carbon, so it's got some hydrogen in it, it's got some oxygen and other things. Let's quibble about this small amount of other things, but let's just say it was made out of carbon. Let's say you got one of those artist's chalks, which are just graphite. So piece of graphite about 200 millimeter long, weigh about 12 grams. So in fact weighs about the same as the atomic mass of carbon. Right, and it is carbon. That 200 millimeter piece of graphite, which is roughly the thickness of a pencil, that has 6.02 by 10 to the 23 atoms in it. Okay, remember how many grains of sand that is? 500 trillion cubic meters. Okay, so just think about that. You will probably not come across a beach anywhere with that much sand on it. Okay, so 500 trillion cubic meters of sand of sand would be just this amount, just this 1 mole. Okay. All right. So that will give you an idea about how small we are talking about when we talk about now. When you see that 6.02 by 10 to the 23, so look at that number 23, and then think about what it must be, how small it is if this thing is negative 31. So this is 9.1 with 31 zeros backwards. Okay, so 31. How small is that? I mean, that is so incredibly small. It's 31, and that is the mass of just 1 electron. That's why we don't care about the mass. This is still pretty small though, minus 27. So it's still quite a small amount. Many zeros backwards, 10 to the minus 27. So it is still, a proton is very small. However, the point about that is this. Because the 22.7 litres of helium at sea level and 0 degrees weigh 4 grams. That's the important thing. The important thing is we now have reduced the amount of helium. The amount of helium, we've reduced that to grams. We've reduced that to mass. We now understand what mass actually is. So let's see if we can put that into a statement. Mass is the total sum of all the protons and neutrons in an object. How much does this weigh? This weighs as much as all the protons and neutrons in this object. That is what we mean by mass. Okay, hope that helps. If you like my videos, please press the like button or the dislike button if you didn't like it. And if you didn't like it, press it many times. You know, really smash that dislike button, no problems at all. And also, if you haven't subscribed and you want to see the rest of this, so that we've looked at mass, so we're going to be looking at gravity. So I want to introduce you to Newton's gravity and also Einstein, and show you how these things complement each other. And then we'll be looking at force, acceleration and motion in general, and we can see how it is that we can use these things to be able to make predictions. Like, for instance, if I was to throw this pen up in the air, I can predict exactly how fast it'll go up. I can predict how fast it will take to hit the ground. Okay, I can predict how high it will go up. Okay, there's a whole bunch of stuff. If I'm shooting a missile in the Navy and I'm shooting a missile at a ship, okay, I know where the target is. The radar tells me where the target is, tells me what the distance to the target is. I can work out exactly, if I know what the ballistics velocity is, then I know exactly when it's going to hit that target. Okay, and if I'm not sure of where the distance is, then I can calculate that distance. All right. Now all of these things are possible because of gravity and acceleration, of course. Because when we're talking about that sort of stuff, we're talking about two vectors. We're talking about a vector that's a horizontal vector, and we're talking about a vertical vector. Okay. All right. So. Once again, press those buttons please, and then I'll do the rest of these. Okay. Alright, see you next time.